Hello, welcome back. So, in the last class we discussed about lubrication approximation. So, today we are going to discuss a similar application which is popularly known as a squeeze flow. So, as the word indicates, I am sure you would have experienced a squeeze flow in a variety of applications in real life. So, typically squeeze flow has applications in devices where you have such configurations. So, there is some material and then you apply some force. So, then it gets squeezed and then you get due to the corresponding flow you get the corresponding liquid like this. Okay. So, there are a lot of applications. So, in particular filters and then some industrial dampers and where typically lubrication plays a vital role. Okay. So, today we are going to discuss about the squeeze flow. Okay. So, as the configuration indicates, so we are going to consider such configuration. So, where we consider a Newtonian flow within this. Okay. Of course, this example I have taken from something non-Newtonian flow, but today we are going to discuss about Newtonian flow bounded between two circular discs, and then the lower disk will be stationary and the upper disk is exerted by some force. Okay. So, let us formally understand the problem. So, the problem is we consider incompressible Newtonian fluid between two parallel discs of radius r separated by a distance h, and we are assuming that r is much larger than h, and as I already indicated, the upper disk is subjected to axial force. So, typically when we say vertical, so it is positive direction. So, since we are pressing the disk, so it is taken as a negative. Okay. So, this is a negative z direction and the lower disk is stationary and the flow is assumed to be symmetrical in the azimuthal direction. So, this is nothing but axisymmetry. Okay. So, let us look at the configuration. So, since we are discussing as two plates, so these are assumed to be circular, but for configuration wise they are indicated like this. Okay. So, we are assuming that the plates are located at z equal to 0 and z equal to h. So, we have the corresponding geometry here. So, this is r and then this is z. Okay. So, with this configuration, so this plate is stationary and then the disk. So, this is velocity is given in this direction. Okay. And we are assuming Stokes flow with viscosity mu. So, since we are considering a steady Stokes flow, so we have corresponding equation of continuity and then momentum balance. So, for the cylindrical configuration with the axisymmetry, we write down the equations in component form. Okay. So, this is the equation of continuity. As you can see, there is no V theta term because of the axisymmetry assumption. Now, let us look at the r momentum. So, r momentum, you can see there are no derivative terms with respect to theta, that is again due to the axisymmetry assumption. Okay. So, already we have discussed these equations in some of our previous lectures. So, one can refer for the full system of Navier-Stokes equations in cylindrical coordinates. From there, if you apply axisymmetry, we get this is the r momentum, and theta momentum, this is redundant because all the variations with respect to theta are 0. So, we get the corresponding u theta is 0. So, therefore, we get this corresponding pressure derivative is 0. So, this immediately indicates that pressure is function of r and z only, and finally, we are left with the z momentum equation. So, which is given by this. Okay. So, this is the basic assumption. So, now if you see, we have radial velocity and we have axial velocity. So, we would like to know for this configuration, since we are assuming r is much larger than the distance between the plates discs. So, what kind of competition between V r and V z, and which is more prevailing compared to the other. So, these one has to analyze. So, this is possible via the corresponding order analysis. So, correspondingly we introduce some scaling arguments. So, we know that vertical velocity is of order v. So, therefore, we first normalize the axial velocity with v, and then radial for the time being, let us say it is a v star, which we would like to estimate, and then r is radius of the disk, and z is normalized by the distance between the disks and the pressure as usual, which we have used. Okay. So, now let us consider our two terms in the equation of continuity. So, you can recall. So, this is one term and this is another term. So, correspondingly, if you see this, so you have an r there and a derivative. So, ultimately this will be of order v star by r. Okay. And similarly, this if you introduce this scaling, so this will be of order v by h. Okay. So, now so these are the two terms in our equation of continuity. So, from this one can conclude that v star is v times r by h, and r is much larger than h. So, this indicates that the radial velocity is substantial. Okay. So, because r is much larger than h. So, this indicates that the radial velocity scaling is substantial. Okay. So, that is our conclusion. So, radial velocity is substantial, hence we assume to be function of r and z. So, now let us get some estimates on the axial velocity. So, we have one can note, because already we have indicated here, and so v is of order 1. So, then you can see, so this is finite. Okay. Because this is comparable. On the other hand, if you consider this, this is of order v by r, and this is of this order. So, now our assumption is r is much larger. So, therefore, this goes to 0. Okay. So, that means the radial variations of the axial velocity are almost negligible, because r is much larger. So, hence our conclusion of V r is substantial has to be supported by some conclusion on V z. So, that is nothing but V z is function of z and maybe a weak function of r, which is negligible. Okay. So, that is so in some sense the corresponding lubrication kind of approximation is indirectly reflected in this fashion. Okay. So, we go with the V z as a merely function of z alone and try to proceed with the analysis. Okay. So, if you can visualize, suppose you have two discs and then pressing. So, you can visualize. So, the flow gets like this. So, radial velocity has a lot of importance in this problem. Okay. So, that is what we have seen it mathematically. Okay. So, now under this assumption, how the model gets reduced. So, the above arguments, this is already we have concluded axial velocity is function of z alone. So, then from incompressibility, that is conservation of mass, that is equation of continuity, we can obtain this. So, this is very straightforward. So, let me, so we have the reduced conservation of equation under axis symmetry. We have already seen this plus equals to 0, and then this V z is function of z, that already we have seen. So, this implies minus r. So, this I can write it as because it is function of z alone. So, now we integrate. Okay. So, plus a function of z. So, this implies okay, but we need a boundedness condition. So, that is V r is finite at r equals 0. So, this indicates so, therefore, what we get is simply so, the incompressibility condition has given a this is function of z. So, radial velocity is linearly depending on the radial distance. So, that is a inference from this relation we are getting. So, any case we are going to use this for further analysis. So, that is what I have indicated here. So, this is what the incompressibility assumption. So, now we have to get the corresponding momentum equations. So, again here it is very easy to observe. Please pay attention to the corresponding r momentum equation. So, we have obtained V r is some constant, that is function of z times r. Okay. So, so therefore, this is r in the numerator and r square. So, this is 1 over r. Okay. Similarly, here whatever r is left with this derivative, that is nullified. So, then this interior is of order r, and again that is nullified. So, this is 1 over r and here 1 over r, the constants remain. So, therefore, this complete combination is 0. It is very easy to calculate. Okay. So, correspondingly V z is already we have seen it is function of z. So, therefore, this term is also 0. So, that is what we have written here. So, this is r momentum reduced to dp dr is this, then on using this relation one can write. Okay. Then the corresponding z momentum equation is correspondingly given by this. So, now let us say if you take derivative with respect to r. So, then the right hand side will be 0 because V z is function of z alone, right. So, what we do, we differentiate this with respect to r and this with respect to z and write down here. So, from the z momentum equation we get this, and for r momentum equation we get this. So, in combining these two, one can infer that the ODE for V z is this. So, this indicates the velocity structure will be a cubic in z. So, where alpha, beta, gamma, delta are some arbitrary constants that are to be determined, and once we have V z, we can write down V r using the relation that we have. Okay. So, that means at this stage we have obtained the general structure of the velocity components. Okay. So, once we have, so our next aim is naturally to compute the pressure, because in most of the squeeze flows, see the velocity whatever is applied. So, that play a role, and corresponding to that what is the pressure, and then corresponding to the pressure what is the force. Okay. Because most of the times the physical quantity that is of interest is force, which is required to estimate various physical mechanisms. Okay. So, therefore, correspondingly what we do is we first integrate for the pressure and then go for the computation of the force. Okay. So, this is again very straightforward. Okay. So, this is again I can just make you understand. So, we have the R momentum equation which is reduced already. So, that is okay, and we have Vz structure here which is so Vz is written as alpha z cube plus beta z square gamma z plus delta. Okay. So, therefore, if we use 3 times, okay, so what we are going to get this will be minus 3 alpha mu r. Okay. So, this one can just we have to compute the third derivative, substitute, and we get this. Okay. Similarly, we have okay. So, from here we can get mu to be okay. So, this one can calculate very easily. So, that is what we have done. Then we need to integrate. Okay. So, what I have done is mu has been brought. Okay. So, we integrate this with respect to r. So, then you get a function of z, and then you can use this to evaluate that. So, once you do that exercise, you will get this. So, this is again very straightforward. So, we get the corresponding expression for pressure is this, and this constant has to be evaluated. Okay. So, typically the corresponding condition for the pressure is it is taken at the center, typically the pressure is 0, and at the periphery some pressure is given. So, one can take some non-trivial PR at the edge of the disc and then compute, or one can take 0 pressure. Okay. So, now we for the simple calculation purposes, we take H to be 1, and then we are computing PR, that is at the R edges. Okay. So, once we prescribe this pressure, this C can be eliminated and we get the corresponding expression. Okay. So, again this is very simple calculation, okay, because one has to substitute this condition and eliminate C and then substitute back. So, then this can be nicely rearranged. Okay. So, we have now got the pressure, but however, if you see we have the velocity expressions which contains these arbitrary constants, and we have obtained expression for pressure in terms of these arbitrary constants. So, still these arbitrary constants are to be determined. Okay. So, these will be determined subject to the no slip condition on the 2 discs. So, that is the next task. So, the no slip at z equal to h. So, you have vertical velocity is minus v, because we are pushing, and then radial velocity is 0, and at the bottom it is a stationary disc, therefore, V z is 0 and V r is 0. So, then one can use these to determine the arbitrary constants. So, again this is very trivial. So, you should be able to solve and then match with these constants. So, once we have these constants, we have the complete velocity determined. Okay. So, we have the complete velocity determined, right. So, now as I indicated, so we have already obtained the velocity and pressure. So, then the next task is to get the force. So, now typically in squeeze flows, pressure play a vital role. So, one can integrate the complete normal stress to get the force, or get the component of the force that is due to the pressure alone. Okay. So, to start with, we would like to discuss the corresponding force due to pressure alone. Okay. So, this is called a lubrication force, and this can be calculated. So, we are computing between 0 to r and at h equals to 1, considering h equals to 1. So, we are integrating the pressure with the corresponding aerial element. Then we have substituted P r 1, okay, that is computed. So, then one can see, so there is a contribution due to the pressure constant that is provided at the edge, and then there is a component due to the pressure, okay, hydrodynamic pressure. So, correspondingly we have all the value of alpha. So, once that is substituted, we get these two components. Okay. So, this one, if you take P r is 0, this component is not there. So, typically this is termed as the lubrication force. Okay. So, standard expression for the lubrication force between parallel discs is, if you assume P r is 0, we get the force equals to this, but then if we non-dimensionalize, so then we get the corresponding force as 3 pi by 2 r by h cube. Okay. So, this is the competition between r and h. So, here we are assuming r is large. So, therefore, this is a substantial force as well. So, as I already indicated, so if the normal stress component is integrated, one would get an additional component here. So, when I say what is the corresponding normal stress component, what I am trying to say is, so if you integrate P plus 2 mu d v r by d z. Okay. So, this is a normal stress component. So, if you integrate, so from here we got two terms. So, from here we get an additional term. Okay. We get an additional term. So, this is normal stress component should be I think dVr by dz, or so this one has to check. Okay. So, correspondingly we get the additional component. Okay. So, in this case we are not considering this, we have only integrated the pressure. So, correspondingly we are getting two components. Okay. So, this is one and this is the other one. Okay. So, with this we have got the velocity components, pressure and the force. So, the next interesting is to compute the streamlines. So, we fix h equals to 1 and v equals to 1 just for the calculation purposes, and then try to get the corresponding stream function. Okay. So, V z is given by this and V r is given by this, where psi is the stream function, and when we take h equals to 1 and v equals to 1, we get the simplified expressions for the velocity components. So, then one can integrate this to get the stream function. Okay. So, the calculation is very straightforward. So, I am not explaining the integration. So, you can try yourself and see that the corresponding stream function is this. Okay. So, as you can see, so this is streamlines are with respect to the radial distance, they are quadratic. Okay. So, naturally one would be interested in seeing the corresponding contours. Okay. So, how the corresponding contours are behaving. Okay. So, one can use some Mathematica or Maple. So, this is done in Mathematica with a simple command of contour plot with the values shown. So, these are the psi equals to minus 0.2, psi equals to minus 0.6, psi equals to minus 0.8, so on and so forth. But we would like to see what really happens at a closer look. So, these are using Maple. So, these are drawn with you can see much closer denser plot. So, you can see the radial flow going up, and then towards the center it is a more straight. Okay. So, the flow gets radially distributed. So, you are squeezing it, and then the flow is getting distributed. Okay. So, radially, but the radial velocity is very much substantial, not only in radial direction, also along axial direction. So, there is a lot of deviation. Okay. So, this is a very important application in various lubrication equipments, and I hope you get an idea of squeeze flow, and then one can study advanced configurations like squeeze flow of two immiscible flows, or like you have a soil above and then porous soil, and then you are filtering something through a porous pack. So, this is another kind of configuration. So, these are very much useful in various microfluidic environments. Thank you.